Okay, so now we go to number 7. And number 7 has to do with the musical notes. The frequency of 200 CPS, we don't know what note that is. I'm sure it's not a C or a B or anything. But cycles per period, second, it doesn't matter what note is called. The note 1 octave higher has 400 CPS. Is that right? Yeah, that's what an octave means, right? An octave is the interval of musical notes where the frequency doubles. What is the frequency of the note 1 octave higher than that? Because it increased by 200, would it increase by 200 CPS again? And the answer is absolutely not, right? It doubles. Okay, so from 400, what is the double of 400? It's 800 CPS. That's 1 octave higher. And an octave higher would be 1600 CPS. Remember, it is exponential growth and not linear growth, right? So that is how you answer this question. All right, number 8 lists the first 7 Fibonacci numbers. What are the first 2 that will get you started, get you going? The answer, it starts with 2 ones. So 1 and 1, those numbers, I mean, these, the 2 ones will start the Fibonacci sequence. And after that, because this is the formula for Fibonacci sequence. And after that, it's the previous number plus the number before that. That's how you, this is the definition of the Fibonacci numbers. So 1, 1, and then you have 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. Did I get to 7 numbers? 1, 2, 3, 4, 5, 6, 7. Yep. So the 7th Fibonacci number is 13. And at this point, I mean, this will go on forever, but you are asked to list only the first 7. So you are done. All right, the golden ratio is approximately what number? You can make it more precise, but I just want you to know it's about 1.6. That's all you really need to know. I mean, more technically, it's 1.6180339, and it is an irrational number, so it'll continue without any sort of pattern. But just remember, it's like close to 1.6. It's not like 2.3, or pi is like close to 3.14. Nothing like that. Right, the golden ratio is about 1.618, or approximately 1.6. How is it related to the Fibonacci numbers? Okay, so this is an important question. I wouldn't be surprised if you see this question on the final, for instance. Right? How is the golden ratio related to the Fibonacci numbers? And many of you probably will think in terms of, this spiral, because that's the one I drew to give you explain the relationship between the Fibonacci numbers and the golden ratio. So this is 1, 1, 2, 3, 5, 8, and 13, and so on, right? And so this is, and hopefully you've seen that little website where the mathematician or mathematical artist is designing all of these jewelry pieces, based on mathematical notions. And one was the Fibonacci earring, which looks like this. I thought that was cute. Anyway, so this, how is it related? Well, technically, this is what you should do. You should say that this is the limit of the ratio. Let me just go ahead and write this down. Okay, so the precise answer is this. Phi, the golden ratio, is the limit of the ratio of 2 consecutive Fibonacci numbers. So for instance, it's 13 divided by 8. That's a number close to Fibonacci numbers. The next one will be 21 divided by 13. That's even closer to the golden ratio. And so if you take 2 consecutive Fibonacci numbers and take the ratio of the bigger one divided by the smaller one, as n gets bigger and bigger, this means n goes to infinity. As n gets bigger and bigger, the number, the ratio becomes closer and closer to that golden ratio phi. Okay, you can also say this in English in a little more casual way. You can say the golden ratio is what the ratio of 2 consecutive Fibonacci sequence approaches. Okay, in other words, the ratio of two back-to-back Fibonacci numbers tends to approach or approaches the golden ratio. Okay. Now, if you drew this picture and if you say something like the ratio, when you make this the Fibonacci spiral, then the ratio of this to this, the longer side to the shorter side, becomes closer and closer to the golden ratio. That would be okay. That would be acceptable because the golden ratio really is the limit of this length divided by this length as you continue to make this spiral bigger and bigger. Okay. Number 10, compare the energy released by quake A, 3.0 magnitude, and the quake B. Right, so part A, 6.0. What is the energy? How do you compare the energy released by 3.0 earthquake and the 6.0 earthquake? So 6.0 divided by 3.0 would be 2, right? So it's double. No, the answer is no. That's not the way you calculate, right? Because these are logarithmic scale numbers. So the answer to this question is not 6 divided by 3, but 10 to the 6 minus 3. Okay, so that's 10 to the third, which is 1,000. Remember this? Okay, in logarithmic scale, each increase by 1 in the magnitude represents a 10-fold increase. So when the magnitude goes from 3 to 6, okay, then the energy released by the earthquake is actually 10 to the third, which is 1,000 times as big. So you could say quake B, and I'm not going to write the whole sentence here because I don't have space. I think you can see the answer in the more extended answer in the answer key. But you should say the quake B is 1,000 times as big as quake A in part A. All right, and in part B, how about 3.4 and a 3.0? Okay, so then what you will do is you will subtract 3.4 minus 3.0, of course that's 0.4, but then you raise 10 to the 0.4th power. Okay, in other words, you take 10 to the power of the difference between 3.4 and 3.0, and so that's 10 to the 0.4th power. You can use your calculator to find this. And the answer is 2.51 times. So again, it is a little surprise. It's surprising to many people, but a 3.4 earthquake is actually more than twice as powerful as a 3.0 earthquake because of the logarithmic scale, and the Richter scale is logarithmic. All right, number 11. Is the pH level of your stomach acid more than or less than 7.0? And the only thing you need to know, you don't have to know about the hydrogen atom, hydrogen ion or anything like that. You have to know the reference, the reason the 7.0 is given is because 7.0 is the pH level of water, okay? And remember, acidic fluid has a number less than or more than. Yeah, it's less than 7. As the number increases, you get more basic solution. All right. Okay, so hopefully that answered the questions from the art part. There are more questions coming in regards to art. All right, so let's go on. Describe what the Alabama paradox is. Okay, so what is the Alabama paradox? This is hard to write, so let me type it for you. All right, so here's the answer. The Alabama paradox is a situation that occurs when Hamilton's method of apportionment is used, where a state, in this particular case, it was Alabama, but when a state loses a seat in Congress, even though the total number of congressional seats for the country has increased, right? So you've seen the example of this in our handout in our lesson. And so it is as paradoxical it could happen because Hamilton's method basically is assuming that we would just truncate, or we'll just find the the number. You remember that the minimum quota is the so you calculate your quota for a state, and then you basically truncate anything that's after the decimal point, right? And then you look at which state has the biggest decimal part, and that one with the biggest decimal part will gain an extra seat. And when when Hamilton's method is used, because these numbers increase faster for larger states, many times the larger states will be advantageous, and states like Alabama could actually lose a seat when the entire congressional seats go, let's say, from 100 to 101 or something. And so that is what is known as the Alabama paradox. Associate that with Hamilton's method, okay? All right, and by the way, this really happened first time in 1880, soon after the Civil War in real American history. You don't have to know that part, okay? But you should know what the Alabama paradox is, right? As you know, this doesn't happen only in politics, right? If you're talking about the number of nurses or librarians or doctors or whatever, okay, in school district or in hospital district or something, the same thing could happen. Okay, number 13, calculate. Something's not right with my thing here. Let me see what's going on. Okay, so I just discovered that the PDF file I'm using to write my solutions here in this video is a little bit different from what you had. So numbers are off by 1. I think I've just fixed it. Number 13 is the same. Calculate the standard divisor D when 50 lawmakers are to represent 20,000 people. Remember what the standard divisor is, D? This is the first thing you have to find in calculating, in using Hamilton's method. Actually, also for Jefferson's method as well. This number D is the first thing you need to find, okay, when you apply pretty much any apportionment method. And that is the number of people that each lawmaker is to represent. So it's pretty easy if you think about this. 20,000 people have to be represented by 50 lawmakers, legislators, right? So all you have to do is to divide 20,000 by 50. And there, the answer is 400. And so again, try to make sense, not just divide and get your answer. Trying to remember or trying to remind yourself, okay, what does this mean? 400 what? Okay, the answer is 400 people are to be represented by every lawmaker. And therefore, when you have 50 lawmakers, these collectively, they can represent 20,000 because 50 times 400 is 20,000. All right, and then number 14, what's the main difference between Jefferson's and Hamilton's method of apportionment? Okay, so can you tell me what the difference is? The main difference is this, the number D. Okay, so this number D can be changed or modified in Jefferson's method. Remember, that's what Jefferson decided to do or proposed to do compared to Hamilton's. In Hamilton's, it cannot be. All right, so D can be modified in Jefferson's method, but not Hamilton's. So that probably sort of captures the main part of this question here. And in Hamilton's method, you use a decimal portion of the quotas, right? In Jefferson's method, you just keep changing that. Jefferson's method would allow you to reduce D little by little, less and less until the decimal portion or until the minimum quotas will just add up to the total number of seats. Okay, number 15. What is Condorcet method, or what is a Condorcet winner? Okay, so this is the candidate. There's only one if there is one. Sometimes you have none, but the candidate who wins over everyone else in one-on-one comparison or one-to-one comparison. Sorry, I should say. Okay, so if you remember, you can let's say you have A, B, C, D. Okay, if A beats B on a one-on-one comparison, and if A is preferred over C in a one-on-one comparison, and if A is preferred over D on one-on-one comparison, then A becomes the Condorcet winner. Sometimes the Condorcet winner does exist. Sometimes there's no Condorcet winner. And but if there is one, then that winner should be the winner of the election, and that is the method due to Condorcet. All right, number 16, explain how border count method, how the border count method determines the winner of an election. Okay, basically it's a point system, right? Now, if I actually give you a question like this, you would probably have to write a complete sentence or two, and you say a border count is a point system where you get the first place vote. Well, let's see, the thing is we don't know how many, so it's hard to write. But the let's say not the first place. Let me just say the last place winner gets 1 point, and the second to the last place vote gets 2 points, and so on, right? And then you just add up all the points for every candidate, and whoever has the highest number of points is declared the winner. Okay, that candidate with most points wins. That is the border count. I didn't write down the complete answer here, but you can just summarize that in a sentence or two, and that should be your answer. All right, so before you get to 17, which is you have several problems where you actually have to do lots of calculations. Let's take a break, and then when you go to the next part of this video, we will start at number 17 and go to number 21.